Good afternoon and welcome to the second lecture of Advanced NMR Spectroscopy Part 1 course. So, yesterday I discussed about the resonance and detection of NMR signal using a quantum mechanics method as well as the classical mechanics model. So, which I have shown here is that the if you see that when you apply the magnetic field, the magnetic field is applied along the z-axis, and once you apply the field along the z-axis and you put the sample into the field, there will be a distribution of the spins between the two states, and equilibrium will reach after a certain time, and that I have told you how it is governed by the T1 relaxation. So now you will see a resultant magnetization M, which is shown here. And then if you put a rotating magnetic field B1 in the XY plane, which is rotating at the same frequency of the precessional frequency of the nuclei, and with a magnitude of B1, then you will see that this individual magnetic moment will sense this, and they will try to undergo a phase coherence and the bundle up. So during this bundle up also, the magnetization also tilts, so that you will have a magnetization component in the XY plane, and that can be detected by the detector. And this the flip angle, it depends on the magnitude of the B1 as well as how long this B1 is applied. Okay. And if the flip angle is alpha, the magnetization in the XY plane can be correlated. So M XY is equal to M sine alpha. So that M is your equilibrium magnetization. Now that this M XY will oscillate in the XY plane, and it will generate the NMR signal. Now you can see from this equation that the signal intensity will be maximum when sine alpha is equal to 1, that is when alpha is equal to 90 degree. Now if you remove the B1, then you will see that this M XY component goes back to it will not go back to the Z axis instantly. It will take some time. So what will happen during this time? The first, this M XY component magnetization will lose their phase coherence by spin relaxation. That is called the T2. And simultaneously, there will be also this, the T1 will also be effective. And finally, all the spin will again go back to the equilibrium state, and the magnetization will go back to the z-axis. And if it is seen that the T1 is normally greater than, slightly more, it's greater than T2. So that is the thing yesterday I told. Now let us see that how small how a small field. You see, this B1 is a very small field. How it can tilt the magnetization from z-axis. This magnetization is placed in the z-axis because of the external magnetic field is placed along the z-axis. Now, if you see that, so this is your magnetic field B0 along the z-axis, and now you will be putting the B1 magnetic field along the x-axis. So when both are absent, the B0 and B1, you will see that there is no net magnetization. So it will be said that so there is no net magnetization. But as soon as you put the B0 on, you will see that there is a development of the Z component magnetization, and you will get finally equilibrium magnetization after a certain time. So that is called the M. Now, if you put B1 on, okay, so that now you saw the M is along the Z-axis, okay, and it is totally held by the external applied magnetic field B0, okay. Now you are putting a radio frequency field of magnitude B1 along the x-axis. Now I would like to, one thing I want to tell, this B1 is nothing to do with the radio frequency. Okay, it is actually the magnetic component present in the radio frequency wave, okay, or radio frequency radiation. So it is nothing to do with the frequency. So the frequency can be different. Okay, it is rather the amplitude of the radio frequency wave that gives you the B1 field. It is related to the amplitude. Okay, so this is B1 is nothing but it is also a magnetic field generated from the radio frequency, and it comes in millitesla. If you see, the B1 is in Tesla, whereas the B0 is in Tesla, but B1 is in millitesla or even less than that. So what will be now, if you, there is a static observer in the laboratory axis system, what that static observer will see, that it will see that when you put this B1 field, this M will not start processing along this x-axis where you are applying the B1 magnetic field, B1 field, and this precision will be in the ZY plane. So automatically the M will be tilted towards the y-axis. Okay, and that tilting frequency will be omega 1 is equal to gamma B1. Gamma is the gyromagnetic ratio of the nuclei which you are observing, and B1 is the field strength of B1 field strength. And as I told you that as the B1 is very small compared to the B0, so omega 1 will also be very, very small compared to omega 0. And you will see that this omega 0 is in megahertz, where you will see that omega 1 is in kilohertz. Okay. Now, if you apply the B1 field for a time so that it gets tilted to 45 degree, you will get that M will precess like a cone. And if you give a B1 for a duration so that it comes to XY plane, you will get as a describing, so that this precision will describe as a disk. Okay. Now let us. So we saw that this is the laboratory framework. So what we saw that there is this M is now processing under the applied field. The XY component is also processing, and the B1 is also processing. So there are several components which are rotating. Okay. So when in such a situation, it makes the system brings the complexity in the system for analysis. So what we will do now, we will introduce a new system or new frame called rotating frame. So what is rotating frame? What we will do that in the rotating frame, we will now rotate the XY axis. Okay, so they will be rotating clockwise around the Z axis with the frequency, the Larmor frequency or the Larmor frequency of the nuclei. So now instead of, so what is happening? So that now this X and Y axis are rotating at the same frequency of the nucleus is was rotating. So what will happen? So if you do that, you will see this now M is all becomes stationary. The B1 also becomes stationary, and MXY also becomes stationary. Okay, but you will see the whole, if the person who is observing, you will see the whole system is rotating. Now suppose if that the observer is also rotating at the same frequency, let us say he takes a position along the y-axis. So you will see that the whole system is now stationary. So you can see that the whole system now looks stationary, and the rotating coordinates are now represented by X prime, Y prime, and Z prime. So we are moved from a laboratory static framework to a rotating frame system, where your coordinate system is rotating with the precisional frequency, and that makes the whole thing, all the things which were rotating earlier now become stationary. Okay, so we found that all these things become stationary. Now what happens to B0? Whether this, when you move from the laboratory's stationary framework to a rotating framework, what effect it does to the B0? Okay, So what you will see that in the rotating frame, the M does not feel the full effect of B0, but rather a reduced magnetic field B prime. I will tell this way. Let us say you initially your precessional frequency was omega 0. Now your framing is also rotating in the same frequency. So what will be the and so automatically with respect to this rotating frame, your precessional frequency will be 0. So what that tells that there is no effect of B0 because now the precessional frequencies become 0. So automatically it equals means it means that the effect of B0 is nullified. So that means if you start rotating the coordinate system, you will see that there is a reduction or the effect of B0 is getting reduced, and that reduced field is given a name B prime. Okay. So what is B prime? So B prime will be now B0 minus omega RF by gamma, where omega RF is the angular frequency of the rotating frame, and gamma is the gyromagnetic ratio of the nucleus we are observing. Okay, so this omega RF by gamma is also equivalent to a magnetic field is BF, and this is called the fictitious field. So automatically this fictitious field is generated or existed due to the relative motion of the coordinate system, which was not there earlier. So if you compare now with the fixed coordinate system, so for fixed coordinate system, omega RF is equal to 0 because frame is not rotating. So the magnetic field B prime and B0 are same. But when you your frame is rotating with a precessional frequency of the nucleus, you will see the B prime becomes 0. That means the effective field experienced by the nucleus becomes 0. So this is a very nice thing which has happened due to this movement of the this coordinate system. Now again, I have done a little bit of mathematical manipulation here. So we know the gamma, the gyromagnetic ratio can be expressed by omega 0 by B0. And if you put this thing here, so B prime is actually can be now expressed in terms of the precessional frequency of the nuclei under the applied field B0 and also the rotational frequency of the coordinate system. Now what you do, you turn on the radio frequency field B1. Now as the system is rotating, so your B1 is fixed along the x dash axis, and rotating frame, this system is static along the x prime axis, and also it is also perpendicular to the B0. So automatically now you have a radio frequency field which is static, and also you have a reduced field due to this motion of the coordinate system a B prime. Okay, so you can express because now you can consider this B prime and B1 as two vectors, and you can find out what is the value of the effective field. So that B effective will be B1 B prime square plus B1 square under root. Okay, so automatically, so this is nothing but your vector algebra. So so see, if B prime is 0, it is only B effective is B1. Okay, but let us say there may be a condition that B prime is not 0 exactly. Okay, so you will get a effective field. Now, what will be the position of this effective field? Whether it will be in the Z direction or whether it will be in the X prime direction or anywhere between Z prime and X prime. So that one can very easily find out from the relation that the tan theta, the angle which forms this B effective forms with the Z axis, can be found out by trigonometric relationship. It is B1 by B prime, and automatically this B prime is, which I have already shown here, the B0 into 1 minus omega RF by omega 0. Okay, now we know that B0 is much greater than B1. Okay, now there could be two situations. Okay, one situation is that omega RF and omega 0 are very much different. Okay, Let us say one case, this omega 0 is much greater than omega RA. Okay, then you will see that tan theta is 0. That means the B effective will lie along the Z prime axis. Other situation is that omega RF is very large than omega 0. Then you will see the B effective will be along the minus Z axis. The second situation is that if omega RF is equal to omega 0, the tan theta will be infinity. And when tan theta is infinity, theta is equal to 90 degree. And automatically you will see your B effective will not now lie along the X prime axis. Okay. So that means the effective field will be along the X prime axis. And now the nuclei will presses along this new magnetic or effective magnetic field, and the precessional frequency will be omega 1 is equal to gamma B1, because now B effective is equals to B1, because the B prime has now become 0. So this situation is called the resonance condition in rotating frame. Now, due to the rotation of the coordinate system, the effect of external magnetic field is almost nullified. Hence, B1 is now effective. So initially, now you see the B1 is very small, but still it can do its job because we have nullified the effect of B0 field due to the rotation of the coordinate system. Now that I have already told you that this B1 causes, because once your B1 is in the X prime direction, so automatically the magnetization will now presses along this X prime. Automatically it will be in the Y dash Z dash plane, okay, which I have shown here, okay, and when this rotation or movement reaches to the then when this M reaches to the Y prime axis, the angle is pi by 2. Okay, when this alpha is 180 degree, this magnetization reaches to minus Z prime axis. So it depends on how long you are putting the B1 field. So it depends on the B1 field strength as well as the time. Okay, now so the situation I have shown here. So now you have initially, now you have, this is your equilibrium magnetization, and you have now turned on the B1 field. So the magnetization now rotates and it comes to the XY plane. And let us say, and then you turn off the B1 field. Sorry, you turn off the B1 field. Then what will happen? Is all this magnetization will now again go back to the Z prime axis, following both T1 and T2. So first it will decays in the XY plane by spin relaxation, and simultaneously there will be T1 relaxation. Now let us see how we can use this rotating frame system for detection of signal in continuous wave NMR, CW-NMR. Okay. So now if you see in a NMR sample, it contains many nuclei with many precessional frequencies. Okay. And if you remember that this in CW-NMR, these frequencies are detected one by one. So what you do, either you change the magnetic field or you change the radio frequency field. Okay. So if you think that you can think the equilibrium magnetization can be a sum of all magnetization coming from each and individual spin components. Like M1 is from the spin component 1, M2 is from, so that the total Z component magnetization is sum of all these magnetizations, where this Mn represents the equilibrium Z component magnetization due to nuclei N. Now, what you do, you keep the rotating frame frequency at radio frequency is same. So your omega rotating frame is equal to omega radio frequency, and B1 is now applied along the x prime axis. So now B1 is static along the x prime axis. Okay. So what you will see that spins having this the precessional frequency equal to the radio frequency equal to the rotating frame frequency. Now there will be a phase coherence, and due to this magnetization, Z component magnetization will tilted from the Z prime axis towards the Y prime axis. Okay, and then you will get a XY component of magnetization which can now be detected. Okay. So, and now if you see in NMR, what you do that now you are changing, either you sweep the radio frequency or you sweep the magnetic field. So when you are sweeping the magnetic field, so these resonance conditions will not be there. Once you change the magnetic field, so that means this resonance for a nuclei happens only for a very short period. So as soon as you changing the field, this resonance condition will not be there. Okay, so then once the resonance condition is not there, you will see those spin due to Mn now will go back to again to Z prime axis following T1 and T2. Okay, so if you do this sweeping in this way, and you can bring all the resonances, all the nuclei into resonance one by one. So that is the way your CW NMR works. So this is the functioning of continuous wave NMR in rotating frame. Okay, so now so how this rate of change of this, because we are now detecting the signal either in the XY plane. So in the XY plane means you will see a magnetic component changing with time. Okay, in the Y axis. Okay, or Y prime axis. Okay, so when this happens in the laboratory frame, that is your Y axis. And if you see that these are called the block equation. This block has developed as a derived mathematically what will be the rate of change of Y component magnetization with time, or Y prime component magnetization with time, and that I have given you. So in case of Y component, it will be directly related to the gyromagnetic ratio, the initial Z component magnetization, the B1 field strength, and it is the precessional frequency, and this is the time for how long the B1 is applied, and this is your X component magnetization, and this is your magnetic field, and this is the Y component magnetization, and this is your T2, and all these derivations are available in many NMR books. So I will not go through the mathematics for that. So this is the equation. Similarly, a similar equation in the rotating frame, but you will see that that is slightly different. So there it is the involvement of omega and omega 0, where the omega 0 is the normal frequency of the nuclei under applied field B0, and omega is the frequency of the varying radio frequency field. Okay, so automatically you can see that when this is different from, you will let us say when omega 0 and omega are same, that means they are in perfect resonance condition. When they are different, they will not be, they will be out of resonance. So there will be a difference in the signal. And if you place the detector in the y-axis, the detector signal intensity is also given here, where the my prime is related to the various parameters. As I told, this is the your Z component equilibrium magnetization M0. This is the gyromagnetic ratio. This is the B1 field strength, and then all these things T1 and T2. Okay, so all these informations are available, so you can find out what will be the signal intensity along the y-axis. Okay. Now we'll come. So we have seen that so far we are changing the things slowly. Okay. Now we would like to in case of pulse NMR spectroscopy, instead of giving the B1 field for what we will do, we'll give the B1 field for a very short time. Okay. So before we do that, now I will just again remind you that B effective, which I have told you. So B effective is the combination of the reduced field, the B prime, and the B1 field, which is generated from the radio frequency. So and this is your vector addition. Vector addition. So you can get it from the vector addition. Now you see that again the same thing which I have discussed, that that this B effective will take a position in the coordinate system depending on the values of the this B1 and B prime. So if the so there is one condition called the on resonance pulse. That means in the under the on resonance pulse, your radio frequency field, the rotating frame frequency field, and the omega 0, that is the your precisional frequency, they have the same value. And if that happens, then your B prime 0 is equal to 0. Then only your effective field is the B1. Okay, and this is called the on resonance pulse. Okay. Okay, and then you will see that under this on resonance pulse, the effective field is equal to B1, and it will lie along the X prime axis. And once this field is there along the X1, the magnetization which was there along the Z axis or Z prime axis will not start precessing, and the precisional frequency is equal to omega 1 is equal to gamma B1. Okay, so this which I have shown here pictorially, that once you apply the B1 field, the M1 the magnetization will not start precessing, and it will and if you keep it on, or if your duration of the B1 is such that it reaches the y-axis, this we call a pi/2 pulse. And if your duration is such that it reaches to minus z-axis, we call this is a pi pulse. Okay. Now let us say if the radio frequency pulse is applied for a period of Tp. Okay, so we are now giving the B1 field for a particular time. So that is called the Tp, and the angle through which the M will rotate will depend on the alpha will be omega 1, because omega 1 is the precisional frequency and this is the time. So alpha will be omega 1 is into Tp, and omega 1 is nothing but gamma into B1. So this alpha is called the flip angle of the pulse. Okay. So if Tp is such that the pulse duration is such that it will rotate the M to 90 degree, we call this is a pi/2 pulse that I explained to you. And if you keep it, if Tp is such that M rotated by 180 degree, so that it will reach to the minus Z prime axis, it is called a pi pulse, or also it is called a inversion pulse. So now, if you for a flip angle of alpha, so what will be your magnetization along the Z axis and the Y axis? So this is your flip angle. The magnetization has now tipped away from the Z axis towards the Y axis, and this is the angle. Okay, so how that is related? So the Z component magnetization. So this is your magnetization. It will have a component in the Z axis also and Y prime axis also. So the Z prime component will be M0, the initial magnetization, into cos alpha, the angle which how much it has been rotated. Similarly, the Y component magnetization will be Y prime is equal to M0 sin alpha. Now we have seen that the condition when we are using a on resonance pulse. But if you record your when we record, you take a real NMR sample, you will see that there is not only one nuclei present. You will see a large number of nuclei present. Okay, so when you have a large number of nuclei of different resonance frequency, okay, then how to bring all these things, this magnetization, how we can rotate all this magnetization together, okay? Because we cannot be on resonance with all the frequencies at the same time. So how can we achieve a condition that all frequencies resonate at the same time? So for that, what we will do, we'll use a pulse called hard pulse, okay, of a chosen radio frequency. So we will select one of the radio frequency. So there are several frequencies. We will choose one radio frequency, and I will tell which radio frequency we will choose. Not necessary from the frequencies which we get the NMR signal. We can select any other frequency. So now you choose one radio frequency and you use a B1 field, which is very strong, okay? So that the B effective is much larger than the B prime. So as all the nuclei do not have the same frequency, so this B prime will not become 0, because B prime will be 0 only when all the precessional frequency will become 0. But that is not possible. At any applied magnetic field, each nuclei will have a different precessional frequency. Okay, so there will be always a B prime. So your B1 field should be strong enough so that the B effective will be much larger, and it will bring and the B effective will lie along the x-axis, which is required for our resonance condition. Okay, so then the B, if the B effective is B1 is very large, then B effective will be B1, and the tilt angle will be 90 degrees, so that the B1 will be along the x-axis. And when you apply this B1 field, the magnetization will now rotate along the YZ plane with a precessional frequency of omega 1 is equal to gamma B1. Now, as the field strength is very high, all the frequencies, all the M1, M values, or the equilibrium magnetization will rotate. So that is the condition we are using the hard pulse. Now, if you consider that in terms of frequencies, you consider, because there are a large number of frequencies, this condition translates to omega 1 is much greater than the offset of frequencies over which the resonance of other nuclei appears. The offset means you will see you will have a particular frequency. There will be some frequencies which will have a higher value, or some frequencies which will have lower value. Okay, but as we are using a very high strong B1 field, all these things we are able to rotate into the XY plane. Okay, now I have given one example here so that it will be very clear to you. Now let us take a 1H NMR spectrum which is covering let us say around 10 ppm. Okay, let us say from 0 to 10 ppm. Okay, and see that the peaks are now in the both sides. Okay, some 2 peaks are below 5 and 2 peaks are above 5 ppm. Okay, anyway, I'll tell later on what is ppm. In the next lecture we'll start the chemical shift. Okay, so now what you do, if you put the transmitter frequency is nothing but your radio frequency, and that you put at this frequency which corresponds to the 5 ppm in this scale. Okay, so now you see that your peaks are in this side 5 ppm and this side 5 ppm. So you have only offset of 5 ppm. So if you, let us say you are using a spectrometer of 500 megahertz, then total offset will be 2500 hertz in each side. Okay, so it will be 5 ppm into 500 hertz per ppm. That I will tell later on how we are getting this 500 hertz per ppm. Okay, that we'll discuss later on. Okay, so you have a offset of 2500 hertz on both sides of the transmitter frequency. Okay, and if you convert this hertz into radians per second, you multiply this with 2 pi. Okay, so it becomes about 1.6 into 10 to the power 4 radians per second. Now let us see normally if you see in NMR spectrometer of 500 megahertz, you will see a 90-degree pulse length is about 8 microseconds. So that means in 8 microseconds, your equilibrium magnetization moves from Z prime axis to Y prime axis, because that is 90 degree. Okay, so let us see. So the alpha we know it is 90 degree, and TP also we know 8 microsecond. So what will be the omega 1? So omega 1 is equal to alpha by TP. So alpha we know this is 90-degree pulse, so it is pi by 2, and we know the length of the pulse, it is 8 into 10 to the power minus 6 second. So you get the omega 1. The radio frequency field is about 1.96 into 10 to the power 5 rad, whereas your required field, the offset field required is 1.6 into 10 to the power 4. Okay, so what you see is that the radio frequency field is 12 times greater than the offset. So you can very easily actually excite all the frequencies together. Okay, so this is the trick which is used in pulsed NMR, so that you use a very strong B1 field and for a very short time. Okay, see, if you reduce this pulse duration later to 1 microsecond, you will get a better, a higher omega 1. That means you will have a better, stronger field. Okay. And normally you'll see this 90-degree pulse for in many machine it is between 5 to 20 microsecond. Now, if you want to see that, we saw that in terms of the field. Okay. Now we can see that we can consider that the hard pulse is as a polychromatic source of radio frequency, because we know that there are several nuclei they are processing. So, and they have different frequency. So whether this hard pulse also contains the those radio frequencies or not. So what you have to do is that you apply Heisenberg's uncertainty principle. Okay, so what is that? It is delta E into delta T is greater than or equal to H by 2 pi. Or you can just equalize them, so automatically it becomes a delta nu is equal to 1 by 2 pi delta T. And let us say we are applying it for 8 microseconds. So you will see that there is the uncertainty in frequencies. Delta omega is the uncertainty in frequencies is around 1.25 into 10 to the power 5 rads per second. So that means, and if you remember that what was our requirement was, that was, I think it was something in 1.6 into 10 to the power 4 rads per second. And so automatically what you see here, that it can create an uncertainty in frequency over a broad range of frequencies. You see, this is the radio frequency where you have applied for a very short period. Okay, and you can see there is the offsets they have in the both direction of the radio frequency field. So this is called the hard pulse. Okay. Now many experiments you need to excite a selectively to particular nuclei, and then you have to use a soft pulse, okay, or selective pulses. Okay, in that time what you do is that you reduce the field strength of B1 as well as you increase the pulse duration. So that if you see for soft pulses, you will see the pulse duration will be around milliseconds. So it will come around 1 to 100 milliseconds. And if you see that now you can selectively excite a particular frequency, and this you will be seeing that is very useful when you go for specific decoupling experiments, when you have to selectively decouple one particular nuclei without affecting the others. So the basic difference of the hard pulse and the soft pulse is that in hard pulse you use a very strong B1 field, you apply it for a very short period, and you create a uncertainty, large uncertainty in the frequency range. Okay, or you can create an uncertainty in the field that is sufficient enough to bring resonance to the all nuclei which are present in the sample. Whereas soft, you can selectively excite a particular nuclei. Now we'll see that how we detect the NMR signal in a rotating frame. Okay. So again, I am telling you that this the transmitter frequency is nothing but the radio frequency generator. The transmitter frequency is matched with the rotating frame frequency. Okay. So if you do that, and automatically the radio frequency should match with the Larmor precision. Okay, but as we are giving it for a very short time, so what you will see that there will be, see in NMR, as I told you that there will be several nuclei and they will have different precisional frequency. So, and those frequencies we call as offset. Okay. So how this is detected in an NMR machine? So machine also detects these signals, okay, in rotating frame. So what it does actually, the machine receiver. So see, the radio frequency generator is called the transmitter and the detector is called the receiver. So machine receiver frequency is also set equal to the transmitter frequency, okay, which is same but the rotational frequency. So what you actually detect in rotating frame is, so what we are detecting earlier in your static laboratory frame in the XY, now we can detect the magnetization in the rotating frame, and you will see in the rotating frame actually will not be detecting the omega 0, we will be rather detecting the offsets. Okay, and offsets are nothing but your chemical shifts. Actually, that's why you will directly. So the chemical shifts are also can be generated from the rotating frame. So rotating frame makes your life easier, so that your all the things become static, and also you detect the signal also in the chemical shift values. So now here I have shown that how a NMR experiment is done. So there are 3 periods. The first period is that you give enough time to allow the sample to reach to equilibrium, and then you give a 90-degree pulse. So that will bring the the magnetization along the Z axis to the Y axis, and then you switched off the B1 field, and after the RF power is switched off, you will detect the signal which arises from the magnetization, because now as the B1 is turned off, it will rotate in the transverse plane as per its offset. Okay, so now there could be 3 situations. Okay, because of the we have depending on the offset frequency. The offset frequency I am telling you the plus minus delta nu. Okay, delta I am putting because we are now measuring directly in the delta scale. Okay, so this is just nothing a offset frequency. You consider this as some offset frequency. Okay, so now when the delta nu is equal to 0, that means when this magnetization come to Y prime axis, it does not rotate at all. It will remain always in the Y axis, and automatically, and it will decay following the T1 and T2. Now let us say this delta mu is more than 0. So that means that it is moving faster than the rotating frame. Okay. So if this is moving faster than the rotating frame, so you will see a clockwise rotation of this magnetization. Okay. And that will also follow decays following the T1 and T2. Other situation is that the offset is less than 0. That means it is moving slower than the rotating frame. So it will move anti-clockwise at the time progress, and also will decay following the T1, T2. And now I have shown here a situation where, let us say, you have a negative offset frequency where the del delta nu is equal to less than 0. Let us say after the giving the pulse, the magnetization has come to the y-axis. Okay, this you have given a pulse along the x-axis, the magnetization has come to the y-axis. Okay, now you are giving time. So as this is having a negative offset frequency, means it is moving slower than the rotating frame, the magnetization will now move anti-clockwise with time. So let us say when it is in the y-axis, you will get the maximum signal. Okay, you get the maximum signal in the y-axis. Now as it is progressing, then you will see the y-axis signal is decreasing, and when it reaches to the minus y-axis, the x component magnetization becomes 0, so there is no magnetization. Now again, when it keeps on moving, it will be coming towards the minus y. Okay, and like that it will go. Now if you measure the magnetization along the x prime axis, so what you will see that in the along the x prime axis, so when just when the magnetization is along the y prime axis, the x component is 0, and then as x is rotating anti-clockwise, you will see there is a buildup of magnetization along the minus y-axis. That means you will give a negative signal along the x-axis, and then you will see that it will again decrease, and finally it will become positive. So when the y component magnetization is minimum, here at is minimum, the x component magnetization is maximum, but it is in negative side. So this is the way so one can put the detector anywhere in the xy plane. You can keep in x prime direction or y prime direction, or anywhere in the xy plane, you will get a magnetization due to this. And your detection is now doing in offset frequency, not the at omega 0. Okay, so this I have shown here that suppose your offset is del delta nu, and you are at after time t, what will be the angle? So initially it was the y dash or y prime axis. Now after time t, it has moved by this much, del delta nu t. Okay. So what will be the full signal, because that was the proportional thing I told. Now what will be the full signal value? So the full signal value will be m y prime will be m0. M0 is that the initial the equilibrium magnetization, and then cos del delta. So this is the offset, cos offset t, the offset frequency into t. In your the x prime component will be negative. If you remember that I was telling that it was negative for x. Okay, it was negative for x, so it will be negative. Okay, and this will change depending on the time. Okay, so if you do the Fourier transformation, you will get a peak due to the frequency and this offset frequency. Okay, so you will get a signal due to the offset frequency. Now if you have a in the spectrum you have more than one line, so what you are doing that what you do at the beginning, you bring the z component magnetization along the y prime axis by applying a pulse, and then if you switched off the radio frequency field, all these nuclei will now start moving in the xy plane as per their offset frequency. So you will get a series of rotating fields in the xy plane, and their position will depend on their offset frequency. Okay. For example, this is for your nuclei 1, this is for nuclei 2 and 3 and so on. Okay, and if you do a Fourier transformation of so automatically if you measure this, you will now get a FID. Anyway, this FID part we will discuss later on. Okay, so ultimately when all these frequencies mix up, you get that is called the pre-induction decay, and if you do a Fourier transform, you will get signals due to this offset frequency values like delta nu 1, delta nu 2, and like that. So that completes your second part of, or the pulse NMR, both using the static or laboratory framework as well as rotating framework. But rotating framework is very handy because you see, due to this, you can detect the signal in a static condition and also in the offset frequency. In fact, machines, all these NMR machine work in this principle. As you know, the receiver frequency, the frequency as maintained at the transmitter frequency. So the signal, either the frequencies are added or subtracted. So if you have any doubt, you can ask me. देखना पड़ेगा ना. Participants,
अनम्यूट कर दीजिए तो सबको.
unmute
कैसे करते हैं? Unmuted, no? Participants? Hello, participants, you can ask directly, you are unmuted, so you can speak out. Or you can write your question in the chat box. Any question?
टाइम लगेगा डाइजेस्ट करते.
So participants try to respond, because accordingly our lecturer will decide how to go about it. Right now, at least you should respond it. इसमें कोई है क्या? यूट्यूब में है, यूट्यूब है और वेबएक्स में. So looks like no question.
So if you have any doubt specifically, I will again tell this thing briefly when I go for like decoupling and other things later on. Okay, I will tell you briefly again. But if you have any major doubts, that these slides will be shared to you. Okay, you can go through them, and then if you have any specific doubt, you can send email. Okay, or you can discuss in the next class.
Yeah, best idea is go through the slides and all our doubts specific doubts, you can write to Professor Ghosh. You have with you, his email ID is already shared with you. So directly write to him. He will respond it in between, or in the next class he will start with this this explanation, and then new things he will be covering. Okay. So we assume that no questions.
This is a very important part, because see, this principle will be used in your 2D NMR and other parts also. So this part you have to understand, and then only your other parts will be much easier. Simple spectral analysis, you may not need this much, but for your other part, you need it. For 2D NMR and multi-pulse experiment, you have to understand what is happening during this pulse and all these things.
As I understand, this is the important part to understand the rest of the things. So this part, you go through the slides, it will be shared with you, and come up with any questions you are having, right?
Share it, make PDF and
okay, then if no questions, then we can stop it here.
इसको attendance
I hope you all have put your registration ID in the chat box, because it is required for your attendance. If not, you please write it quickly. Let them digest it. Read it, this slide.